Imagine a parcel of fluid moving through space. When we apply a force, its velocity changes continuously. The larger the force, the faster the velocity will change. The time it takes for a force to significantly alter the velocity is called the characteristic timescale, which we denote with the Greek letter tau. A smaller tau means a larger force. When multiple forces act at once, the one with the shortest timescale tends to dominate. The same principles apply to continuous processes, like those in rotating fluids. In these systems, three processes shape the behavior: viscosity, inertia, and rotation. Viscosity is a fluid's internal friction, its tendency to resist shear and smooth out velocity differences. Inertia is a fluid's resistance to acceleration, its tendency to keep moving the way it was. Rotation is the average rotation rate of all the fluid in the container. Each process has a characteristic timescale, an estimate of how long it takes to make a significant impact. Here we have a tank filled with water and chia seeds. As we start to rotate the tank, the fluid at the bottom is flung out to the sides due to the centrifugal force. That's the same sideways force you feel in a turning car. Meanwhile, the fluid at the top is almost stationary. It hasn't had enough time to realize the tank is rotating. When the bottom layer of rotating fluid reaches the sides, it has nowhere to go but up. Meanwhile, fluid from above has to descend to conserve mass. This process, called spin-up, is how the velocity of the tank is communicated to the fluid. It depends on rotation and viscosity working together. The lower the viscosity, the longer the fluid will take to spin up. In this experiment, spin-up takes about 5 minutes. After spin-up, all the fluid is rotating at the same rate as the tank. In this experiment, the fluid has already been spun up. Because velocity differences at the boundary and in the bulk of the fluid have been eliminated, viscous forces take a long time to affect the fluid, at least at large scales. Rotation is now the dominant process. We say such a fluid is rapidly rotating. Normally, when we add dye to water, we expect it to spread out almost immediately, but here it seems stuck in place. Why? Think of the fluid like a spinning top. As long as it's spinning fast enough, a top will stay upright as it tries to conserve its angular momentum. A rapidly rotating fluid behaves in a similar way. It tries to conserve angular momentum by aligning its motion with the tank's axis of rotation. Every bit of the fluid acts like its own spinning top. This is known as gyroscopic flow. Because the fluid is fixed, the colors don't spread or mix as much. This becomes clearer if we perturb the fluid. Essentially, we're introducing an inertial timescale. Notice how the fluid mixes, then settles back into equilibrium. You can start to see vertically aligned sheets of fluid forming in the side view. From above, it looks like there's only one fluid layer. This is why we sometimes say the fluid is quasi-two-dimensional. Its velocity doesn't vary along the rotation axis. We can calculate the inertial timescale by dividing the length scale of the ruler, in this case its width, by its velocity. We can also calculate the rotational timescale using the rotation rate of the tank. The inertial timescale is now shorter than the rotational timescale. So is the fluid still rapidly rotating? No. Inertia acted faster than rotation, which is why the fluid mixed. In our analogy, the spinning top fell over because we pushed it too hard. But wait. we know that inertial dominance can't last forever, that the fluid must ultimately settle back into gyroscopic flow. The process behind this change is our underdog, viscosity. While its effects may be negligible on large scales, viscous forces still play a role in damping small-scale motions. As a result, currents tend to occur on larger and larger scales, and therefore longer timescales on average. Let's verify this by recalculating tau u. We don't have a ruler this time, but we can still find it by measuring the rotation period of an arbitrary eddy current. Sure enough, the inertial timescale is once again longer than the rotational timescale. In other words, the fluid is rapidly rotating. The faster we drag the ruler, the more the colors mix, and the longer it takes for gyroscopic flow to be restored. But regardless of how long it takes, rotation always prevails. Timescales are powerful because they allow us to compare vastly different fluid systems, from laboratory tanks to hurricanes, to the oceans, atmospheres, and even cores of other planets. These disparate systems are all governed by the same three fundamental processes. Timescales aren't just helpful numbers for scientists, they're the language we use to describe our world in motion. Thanks for watching.